who is Mattia Donato, who is joining us from the IIT in Genova in Italy, and who will be telling us about a time tagging module for laser scanning microscopes using the BrightEyes-TTM detector system. So Mattia, if you want to go ahead with your presentation, please go ahead.
Thank you very much. Yes, I will talk to you about the BrightEyes-TTM, an open source time tagging module that we made in our lab. So let's start from the image scanning microscopy. The difference between an image scanning microscope and a confocal microscope is that the detector is not anymore a single pixel detector, but is an array detector. That means that you can access a larger set of information, so you will reach a higher resolution, higher signal to noise, and you have also the possibility to perform optical sectioning. So how it's made inside essentially is a confocal microscope in which we replace just the detector. Here in this example, we put as array detector a SPAD array 5x5 represented by this matrix. During the scan, what happens? During the scan of your sample, the detector will see the so-called micro image. So now your data set is not anymore a 2D data set, as in confocal microscope, but is a 4D data set. So you can see it as a collection of micro images. That means that for each single point on your samples scanned, you have a micro image, or you can see as a collection of scanned images. That means that each single scanned image corresponds to the image scanned by the single pixel of your detector. So the heart of the image scanning microscopy is the SPAD array detector. What is a SPAD array? Is an array of single photon avalanche diode that has the features that has a single photon sensitivity, low dark count rate, and negligible readout and very low crosstalk. That means that each pixel is independent from each other. There is not at all a frame rate like in contrast to CCD, for example, and there is a completely asynchronous readout. That means that each detected photon is marked with its spatial and temporal signature. Electronically, you will get a trace, the temporal trace of your photon, practically. Why is important the time? The time is important because in fluorescence microscopy, you can measure it's important to measure the delta time between the laser, the excitation laser, and the photon incoming. If you make histograms of the time interval, you will obtain the so-called fluorescence decay histogram. That's important because with it you can estimate the characteristic time that the so-called fluorescence lifetime that depends by the fluorophore itself and its interaction with the environment, the local environment, so the pH, the ions, and temperature. Essentially, the fluorophore become a probe inside your sample. The question now is how we can acquire such data. Remember, as I mentioned before, we talk about an array of 25 or 49 detectors. During the time that we started this project, there were not a commercial solution for such a large number of channels, but just a solution for a couple of channels that was really really expensive. And okay, you can manage to build up together, but it would be a really bulky solution to put together this kind of device. For this reason, we decided to go for a new time tagging module, the so-called BrightEyes-TTM. BrightEyes-TTM is open source, supports up to 49 channels with a single shot precision of 30 picosecond. To connect to your microscope, of course, has some extra reference channels like a pixel, line, a frame for synchronized to the microscope. Is based on FPGA and is versatile, so and is modifiable and also pretty cheap in comparison to other solutions. On our website, you can find all software and hardware that you need. So from the software point of view, you will find the source code, but also the compiled version. And you will find also the FPGA firmware, so the Verilog and VHDL code. From the hardware side, you will find the list of commercial components that you need. And as I said, it costs, it's pretty cheap, so it's 3,000 euro. And that consists of commercial very available devices like the evaluation board from Xilinx and the USB board to connect it to connect the board to the USB 3. You will find also the drawings and the Gerber files to produce the custom PCB that you needed to connect the detector to the BrightEyes-TTM. For example, here we have one that is TTL solution and the other one that is a LVDS solution. So one of the first tests that we did with the BrightEye-TTM was the so-called single shot precision that consists in feed the one channel of the BrightEye-TTM with something synchronized, strictly synchronized with the laser. The histogram that you obtain is a really narrow Gaussian that, if you fit it, has a sigma of 30 picosecond. 30 picosecond, the question now will be how you can reach 30 picosecond when you have an FPGA that supports maximum 600, maybe 800 megahertz, so something about 1 nanosecond resolution. How is possible to reach it? To explain it, I will go for an example with the objects from everyday life, let's say. Let's imagine that you have a digital alarm. A digital alarm has a resolution of 1 minute. Has a range that is usually 24 hours, and it has a really stable clock. It means that it doesn't lose minutes within year, let's say. So if you assume that it has a really stable clock, it means that the change of digit that we assume here really sharp is really constant. It doesn't change within the time. The time interval between the two change of digit is constant. Okay, of course, if you want to measure the time interval between two events, it is really trivial. You do the subtraction. But then imagine that you have a stopwatch. A stopwatch has a higher resolution, let's say 0.1 second, but has the limit that has a range that maximum is 2 minutes. What you can do for measure something that has a larger interval than that? The trick is to start the stopwatch when an event occurs and stop it when the change of digit occurs of the digital alarm. In this way, you can measure the time interval with a resolution that is about the double of the resolution of the stopwatch. Of course, in the FPGA, we don't have digital alarm stopwatch, but we have something corresponding to it. The digital alarm is corresponding to our system clock counter. So it's a digital simple counter based on 2040 megahertz, so 4 nanosecond as a period. And we use as a stopwatch, let's say, the tap delay line. The tap delay line is a flash DDC and is connected. The start is connected to is triggered by the event, and the stop is triggered by as before, the change of digit, so the rising edge of the counter. What is a tap delay line? A tap delay line is made by delay elements. Inside the FPGA, there are elements, there is circuitry that some circuitry has pretty slow for the FPGA standard. And it actually is something that usually who program the FPGA doesn't like it. But it's actually what we're taking advantage of. So we use a delay elements of 30 picoseconds generated by the so-called carry 4 elements. If you create a chain of delay elements, you form the so-called tap delay line. Everything that you put inside the input of the tap delay line will be propagated inside this tap delay line. That means if you connect to the start event, the event, as you can see here, the one is propagated inside the tap delay line. Then when the stop occurs, you can trigger with the stop a register, and then you take a picture, let's say, of the status of the tap delay line, and once that you have in a register this list of ones, you can reconstruct the TDL value that corresponds. Let's say that shortly, if you count the number of ones that occurs here, you have a value that is proportional to the time between the time interval between the start and the stop. But from the user point of view, how it works? Okay, you can connect the BrightEye-TTM to your microscope. It's a completely passive device, so doesn't modify your microscope. You can connect it from one single channel up to 49 channel, and easily you can download you can stream the data to disk through USB 3. In the first format is the raw data, and that are the so-called we call TTR format. Once that you have the raw data that are not easy to handle, you can convert it through the Python library libttp to the so-called preprocessed data. In this case, you associate to each event laser or photons occurred in the detector. You associate an FPGA, the time in FPGA units. And you associate also to the position, as we talk about imaging, X, Y, and Z. These preprocessed data are not, I didn't mention before, but the tap delay line needed to be calibrated. So after this preprocessed data, you needed to perform the calibration to get finally the data that for each event, you have the time in physical units. Once that you have the calibrated data, you can do what you like with this data structure. And in this example, you can, for example, you can histogram the data, for example, along the time of arrival axis. So you can build a matrix with in which each single pixel has the histogram of the arrival time. Once that you have the histogram of the arrival time, you can perform with your preferred techniques, for example, phasor analysis or a fit, for example. You can extract the lifetime map. And of course, you have also the intensity map. Then finally, you can merge everything together. So the information of all channel all channel by the adaptive pixel reassignment, but you can also use the information that you got with the lifetime of the lifetime. So you can create the so-called FLISM image that code also in the intensity. You see the the photon counting, and in the color you code the lifetime of the lifetime decay. BrightEyes-TTM is not alone, it's part of a family of BrightEyes, and there are other open source tools. I want to mention the BrightEyes-ISM, which is an open source Python library, which is a kind of toolbox for image scanning microscopy analysis. And I want to also mention that this allows, for example, to do optical sectioning, other deconvolution, and other things like that. And this plugin, I want to mention that has also the Napari plugin available. So in theory, let's say, ideally, you can just open the data with Napari and do the analysis directly from the graphical interface. Then there is also the BrightEyes MCS, which is an open source image scanning microscope control software with the live preview, but at the moment is still not released, but we want to release soon. So in conclusion, BrightEyes-TTM is a multi-channel time tagger. It unlocks the full potential of the SPAD array, allowing to perform a fluorescence lifetime imaging scanning microscopy. It's a multi-purpose device, so it's not just for imaging. For example, other colleagues use it for fluorescent correlation spectroscopy or for coincidence. We start to use it. It is an open source software, so from our side, we hope that the community can take full advantage of it and can contribute to its future development. Thank you very much, and I will thank the whole group of Giuseppe Vici Domini.